So this is ECE 341, the 7th online lecture. In this particular lecture, we're going to cover the bivariate Gaussian distribution, which is at the end of chapter 5. And then we're going to work to expand our knowledge of bivariate random variables and extend them to an n-dimensional case. So we'll look at this idea of random vectors. So let's start with the bivariate Gaussian. The bivariate Gaussian distribution between a random variable x and y is a joint distribution, and it's defined by a probability density function. To help us in defining that probability density function, it does help to go ahead and define some variables of convenience. So I'm going to create a variable x prime, which is just my random variable x minus some parameter mu x divided by another parameter sigma x. And I'm going to let y prime be the random variable y minus some parameter mu y divided by some sigma y. We'll find out later that mu x, mu y, sigma y have their standard kind of meaning. They're just means and standard deviations. So a bivariate Gaussian random variable pair x and y has a probability density function fxy that is given using an exponential form. It has a constant up front, 1 over 2 pi sigma x sigma y times the square root of 1 minus rho squared. We'll come back to that parameter rho and talk about what it means in a bit. And then we have the exponential function that's actually going to include the variables x and y, but we'll put it in terms of those variables of convenience, x prime and y prime. It just gets kind of cumbersome in notation if we had all the mu x, mu y, sigma x, sigma y thrown in there as well. So the exp has a minus, right? And then we've got an x prime squared minus 2 rho x prime y prime, and then we have a y prime squared over 2 times 1 minus rho squared. All of that's in the exponent. Out of all of this, mu x and mu y are real parameters, so they're real numbers, and it turns out those are just going to be the mean of the variable x and the mean of the variable y. Sigma x and sigma y are both non-negative real parameters, and we're going to find out they correspond to the standard deviation of x and the standard deviation of y. And then we've got that parameter rho, which we are going to constrain to be on the interval minus 1 to 1. And as you might guess, that rho is going to be connected to the correlation coefficient. Okay, so any pair of random variables x, y that have this joint distribution, right, of that form, that is this exponential of something squared kind of form, we know is going to satisfy our definition of what we mean by bivariate Gaussian. We will see, that's part of the proof and part of the work that we have to do today, that the marginal distributions that come out of this joint probability density function, so fx or fy, and the conditional distributions, such as fx given y or fy given x, whether it's the marginal or the conditional distributions, all of those turn out to stay Gaussian, okay? And you might get kind of an overall point out of this, that it's a bit tough to get rid of a Gaussian. Once you've got that bivariate Gaussian, the other things that we look at related to that guy frequently preserve that Gaussian character. So certainly true with the marginal and the conditional distributions. And so we'll look at that, improve that as well. So we might ask the question, we have this definition of what fx, this joint distribution of x and y is. What does it look like though? Is it something that really does seem to be something that would be how we would view a Gaussian, a bell-shaped kind of distribution? So we're interested in what this fx bivariate probability density function looks like. And we can certainly do that. We're going to go ahead and take some look at some contour plots, all of which I generated in MATLAB. Just to avoid a little bit of complexity, we're going to set the parameters mu x and mu y equaling to 0. If we changed either one of those, we would just move the peak of the distribution. So let's jump over to another application and take a look at that. So I'm going to come over here and look at my bivariate Gaussians. This particular one has a bunch of different cases. I'm just going to kind of zoom in here and look at a few of them in here. So this first one that I'm going to look at, the middle plot here, is a contour plot of that joint density function that we'd previously defined, so fxy, that was based on that exponential. And I've set in here the sigma x parameter equal to 1 and the sigma y parameter equal to 1, and I've set rho equaling to 0. So if we believe what I had said earlier, that sigma x and sigma y are the standard deviations, and rho was the correlation coefficient, What would this tell us? The correlation coefficient being 0 means that one is not linearly dependent on the other. You wouldn't easily fit a straight line fit into this plot. And we certainly see that. What we see here is a bunch of concentric rings. Remember, contour plots, each one of those rings is a particular level of height of that probability density function. So right here in the middle, okay, at the location x equals 0, that's the horizontal, y equals 0, that's the vertical. We have the highest part of this probability density function, and then it rolls off. It gets to some level where everything around that has a particular level, and you can keep going in any direction, and you're just going to go down this hill. So this looks like a bit like a mountain, okay, and it's a perfectly symmetric mountain, and it has a very bell-shaped kind of curve. It definitely gets a little steeper here in the middle, right? And then it starts balancing out towards the bottom, and it starts balancing up on the top. If I were going to cut this guy in cross section, that is, by the way, a conditional distribution, we would see it was shaped exactly like a Gaussian. We'll prove that later. Okay, so this joint distribution just looks like a mountain. And if the correlation coefficient, right, is equal to 0, it's a perfectly symmetric round mountain, right? As long as the standard deviation, the variability, if you will, in x and y are the same. Well, let's look a little bit at what happens as I move that correlation coefficient bigger and positive. So here I have everything else being still the same. So sigma x, sigma y both being 1, and I'm letting the correlation coefficient now be 0.5, midway between uncorrelated, that's correlation coefficient equal to 0, and correlation coefficient 1, where they are perfectly correlated, perfect linear correlation. And what we get is what we expect on this. We do see that now this entire thing takes a particular slant. We can definitely think of a line fitting along the axis of this bivariate density function. As we are following along in some particular value x, if x became larger, let's say a value of 1, we see that it would be correspondingly as likely to see a y being 1 along those lines. And that makes sense. They're positively correlated. As you move in one direction, the other guy should be moving in that. It exaggerates it along that slope of 45 line, okay? Because the correlation coefficient is only equal to 0.5, it does follow a line, but maybe it doesn't follow it very tightly. There's still some variation outside of that line, right? It hasn't collapsed down exactly to a line. We can certainly see what happens as we start moving in limit towards making that correlation coefficient closer to 1. Here is a correlation coefficient equal to 0.9, and what do we see? It's still following along that straight line, which means that as x gets bigger, y gets bigger, right? And it's reduced the amount of variation from that line. So if I knew a value of x, right, the values of y would be smaller than they would have been over here for that same piece of x, something along those lines. So a higher correlation coefficient would help you reduce the variability. If you knew one variable, it would reduce the variability in the other as far as what you would expect. It tightens those contours along the line. If you did rho equaling to 1, I haven't done it here, you would see everything fall right on that line. It would get very, very tight. So it's kind of like we'd expect. We get things that in cross-section look Gaussian, and as the correlation coefficient gets larger towards 1, right, we start approaching that straight line. That means that x and y are linearly dependent, and because they have the same sigma, that line follows a 45-degree slope. We can look at what happens if we start doing negative correlations, right? So here's a negative 0.05 and a negative 0.9. I should have said negative 0.5, not 0.05, so a negative half and negative 0.9. And it's the same thing that we had seen before. It's just now the slope of the line is minus 45 degrees, right? It's a minus 45-degree line because negative correlation means as one thing gets big, right, the other gets smaller. So as x gets bigger, right, what happened to y? It didn't get bigger, it got smaller, something along those lines. And as the correlation gets closer to 1, we see these contours start collapsing towards that straight line between the two. And it's a 45-degree line again because sigma x and sigma y, the variability in x and the variability in y are matched. If I switch down to this next row, this is very similar. We're going to start out with a correlation coefficient equal to 0, but now I'm going to double the sigma y. What does that do? That doubled the standard deviation in y. That said that y is going to have more variation than it did before. We expect things to spread out by a factor of at least 2. If we went back up here and took a look at where those contours went, those contours ended up giving us our final kind of contour up there at about a value of 2. This thing does roll off. These are just like 10% levels. I think there's 10 contours on here, something along those lines. And we take a look at where the last contour that MATLAB picks on this one is. Well, it's at 4, double what we had before. Previously, the final contour in the X dimension, right? It was sitting in there somewhere close to 2, right? And this guy stayed at that value close to 2. So we just essentially stretched things in the Y direction. That makes sense because increasing the variability in Y should stretch things out. It should make bigger values of Y or values of Y further from the mean more likely. So now we don't get like a perfectly symmetric mountain, right? We still get these kind of elliptical things, but they are oriented, right, along the coordinate axes. So your major and minor axes of these ellipses would fall along the horizontal and vertical axes. As I start moving towards having correlation in there, that means that there's going to be some linear dependence between there. So here's a correlation of 0.5 again and a correlation of 0.9. And what do we see? We see these guys starting to fall, a definite line going in there. There's a definite best fit line for these guys. And as one variable gets bigger, so does the other one. And as the correlation coefficient gets closer and closer to 1, that overall set of contours gets closer and closer, right? It gets closer and closer to that line. It begins to collapse down towards that line. Something to notice here. Let's go out on one of these guys like this point right here, right? And so that's at like an x equaling 1. And if I wanted to think about where we would expect the y values to be on that, we could sit there and follow that guy up to where this guy intersects. If I can do this right, I didn't do that very neatly, so let me get it all cleaned up in here. I'm going to try to write these or draw these in neatly. So if I took something like my x equals 1, right, and I look where that went, and I looked at that best line, which is on that axis of the stuff, and I took that guy and put it back, I find out that it comes up not 1 unit, but 2 units. That means the slope of this guy, right, is going to be rising to a run of 1, which is exactly this ratio of sigma y to sigma x. And so what we find is that the slope of the line for this linear relationship is going to be given by the original variability in x and y, by sigma y to sigma x, something along those lines. If I do things by negative correlations, I just get everything doing exactly what we'd expect, except for now the lines have a negative slope, and in that negative slope is going to be a minus slope of -2, right? So it's going to fall 2 for every unit over in the horizontal in there, negative slope in this particular case. We could use all of this to predict the third case that I'm going to give. This third case, I just continue on. I leave sigma x equaling to 1. I now make the variability in y the sigma y 3 times what it originally was, so sigma y equaling 3, and I start out with 0 correlation. What did that do? Things are still sitting out there at the very edge for x at around 2, that's no problem, but the other edge in y is sitting there at around 6, 3 times what we had seen before. So we're scaling everything by a factor of 3. With this 0 correlation, we do not find that there is a line with like a regular positive slope or negative slope, right? This is a series of ellipses that are aligned along the coordinate axes. If I go ahead and start making my positive correlations, 0.5 and 0.9, I just see stuff following along a line of positive slope, right? And for each one of those, as the correlation coefficient approaches 1, those contours get closer and closer, right? Everything squeezes in on that line. If I wanted to know the slope of that line, I could go through and do the same sort of game. I could come out 1 unit in x and see how many units I had to go up in y, and it turns out for 1 unit in x, I had to go up 3 units in y. That's that ratio of sigma y to sigma x again, exactly as I would have expected. Negative correlation, all the same thing. We just flip things around so that they're negative slopes on there. As a final reminder here, and this is what we're going to prove here momentarily, if I looked at something like the marginal distribution, what is a marginal distribution? A marginal distribution might be looking for fx of x. That means I want to find out how x varies and ignore all this stuff about y. So what would I have to do? I'd have to do all this integration, right? Collapse all this stuff down onto onto just the horizontal axis. When I do that, what I get, we will prove this in a minute, is we get just a regular old Gaussian distribution. Furthermore, if I sat there and I said that I wanted to do a conditional distribution, condition on y being some value or x being some value. Let me go to the plot to the left. Suppose I wanted a condition on y being equal to 2. Here is the line y equaling 2. If I wanted to know the distribution of x given y equaling 2, I would just slice this bivariate Gaussian distribution, and I'd look at the profile of what was left over. And here we would see some peak, and if I looked at that in profile, guess what? We would find out in profile when we slice this thing, when we slice this mountain in half along that y equaling 2 line, is that it also would follow a Gaussian shape. That was our original statement, that by using this bivariate Gaussian, if I take the marginal or I take the conditional distributions, they will also be Gaussian. So you slice this guy, you integrate along one variable, everything still stays that bell-shaped curve. Okay, so we should have a better idea of what this looks like. It's sort of like a bell-shaped curve in both directions, x and y. Let's go back to the lecture notes and see if we can finish this out. So what have we done so far? We have come up with or introduced a probability density function that satisfies what we will define as being bivariate Gaussian. It has shape like we'd expect with a Gaussian. It's kind of that bell-shaped curve. It looks like a two-dimensional Gaussian, a two-dimensional bell, a mountain, if you will. And we see that there's an allowance in this definition for having some level of linear relationship between x and y, and that is captured through that correlation coefficient parameter, that rho parameter. Let's go ahead and show that the marginals, so I'm going to show that the marginals, that might be something like fx of x, which we would get from the joint distribution fxy, or the conditionals, which also can be gotten from the joint distribution in a marginal, something like fy given x. Let's show that those are all Gaussian. Turns out that this is not terribly hard, but it is a little bit notationally confusing, and so it does help if I set up some mathematical preliminaries, just notational. It kind of helps things out as we go along. So I'm going to do a few preliminaries here. I'm just going to define some variables. The first one I'm going to define is I'm going to call something mu tilde that is a function of x, and I'm just going to let it be the parameter mu y plus rho times sigma x, x prime. Just going to make that definition. I'm also going to call something else. I'm going to call that sigma tilde, and I can let that be sigma y times this square root of 1 minus rho squared. So two definitions that I'm making because I know where I'm going, and this will notationally just help me simplify some of the results that I'm trying to show. So go back to what our original distribution was. We had our original distribution. I'm going to circle this guy in red. There's our original joint probability density function. And we see some pretty complicated stuff, like in that exponent, there's that numerator term, x prime squared minus 2 rho x prime y prime plus y prime squared. I'm going to do some algebra on that using these variables that I've just introduced. So if I take a look at that, x prime squared minus 2 rho x prime y prime plus y prime squared. That's the numerator of the exponent in the original joint distribution. I can rewrite that. There's an x prime squared. That was, let me go ahead and erase this other one, and we'll just kind of, whoops, didn't want to erase all of that. Let's erase that, and we'll just kind of account for this as we go along. There's that x prime squared in there, and we have a y prime squared, so that's this guy, so that's that one in there, right? We have a minus 2 rho x prime y prime, so a minus 2 rho x prime y prime, something along those lines. That's this guy, right? And then all I'm doing is I'm doing a little give and take. I'm going to add in a little rho prime x prime squared, and I'm going to take it away, a minus rho prime x prime squared. So if I collect terms in this first pair, so if I look at this first pair here, I can pull out an x prime squared, so that's x prime squared times 1 minus rho squared. And then the other one just turns out to be a perfect square, so I can factor that guy out, and it's y prime minus rho x prime quantity squared, something like that. I'm going to call that equation number 1, and then I'm going to look at another quantity as well. So if I look at y prime minus rho x prime, okay, I can also put this in terms of those variables that I introduced. This is 1 over sigma y, and then I'm going to have a y minus mu y minus rho sigma y x prime. I'm going to allow you to go through and make the substitutions and accounting for all of that. It's just turning a factor that we are going to see in the original probability density function, joint probability density, and put it a little bit in terms of these two variables that I introduced, which are going to help us notationally. If I work with this one just a little bit more, I find out that y minus y prime over over itself is going to be able to be rewritten. So this y minus that whole quantity off to the right there is just mu x prime. So this is going to be y minus mu x prime, and it's over a sigma y. What I'm going to do now, because what I was really interested in wasn't just this piece by itself, it was that piece divided by sigma y 1 minus rho squared to the 1/2. And when I do that normalization, I get instead now y minus mu x prime, the numerator didn't change, but by me looking at that sigma y with that other correlation part in there, I can write that in terms of sigma tilde, something along those lines. So I'm going to call that equation 2. Taking equation 1 and 2, I can rewrite my original joint probability density function. I'm going to, again, skip some of the boring algebra on this. You're more than welcome to go through and do an algebraic accounting of all of this if you want. It's just me going back to what was given definitionally as the joint probability density function for a bivariate Gaussian and putting it in terms of these kind of modified parameters that involve a mu tilde and a sigma tilde, and then splitting terms up a little bit. What we get if we do all those substitutions is we can rewrite this joint distribution, right? In terms of the first distribution is going to have something that only has x in it. So I'm going to have a 1 over sigma x root 2 pi exp of minus x prime squared divided by 2. And then there's another term over here that has some y's with a few x's mixed in. But it's a 1 over sigma tilde root 2 pi. And I'm going to have an exp minus a half y minus mu tilde of x divided by sigma tilde quantity squared, something like that. So I'm just rewriting my joint distribution. We're going to use this alternate form, this equation number 3, to help me find the marginal distribution fx of x. And I think when we go through this, it'll become apparent why I was going through this. If you'll notice what happened by me doing this, if I go back up to my original expression up here, there wasn't a really obvious way to split out the x's and the y's from one another. If I look at this numerator term, I got that cross term x and y, so there's just not a super easy way to see that in here. Down here, what I get is I get a product of one thing that looks very Gaussian, by the way. If you just compare that to the standard one-dimensional Gaussian, you're going to see it has exactly the same form. And this also looks like a 1D form of a Gaussian. And we're going to find out that that's exactly what we're going to get on this. So let's use this alternate form to find the marginal distribution fx of x. What is a marginal distribution? Fx of x just takes our joint distribution, that's the fxy, right? And it integrates out the variable of non-interest. So we're going to integrate out y, going from minus infinity to infinity. So we just get rid of the variable of non-interest by integrating it out. So I'm going to go ahead and take this alternate definition, this one right here, right? And I'm going to plug it into there. There's a bunch of stuff in that. I'm going to circle it in blue. There's this part up here that has nothing to do with y, and that means it can be pulled outside of the integral. So I'm going to go ahead and bring that guy outside of the integral. Everything else is left inside the integral, so we are still going to have the integral growing from minus infinity to infinity, and I'm going to have what's left over, and so that leftover piece, right, this guy right here, came from this guy right up here, so that's down there as well. And what I get is I get something out front, that's the blue underline, and then an integral of a mess, but that mess happens to be what? It's just a Gaussian probability density function that has some mean, mu tilde, and some variance or standard deviation, sigma tilde. We don't really care what those things are. We just know that a Gaussian distribution, a Gaussian PDF, when we integrate it, integrates to 1. So that whole integral that I have left over, that's the reason why I did all this notational change. So we could recognize this leftover integral is just the integral of a valid PDF, and it integrates to 1. And that means the only thing that survives, right? The only thing that survives out of this is going to be this first lead part. So our marginal distribution, fx of x, is just going to be that lead piece, which is the one-dimensional Gaussian probability density function. It's a one-dimensional Gaussian probability density function with mean mu x and standard deviation sigma x. So now we definitely know that those parameters mu x and sigma x that were buried into this bivariate Gaussian definition have a physical meaning. They are the mean and the standard deviation, right, of the marginal distribution that comes out of that joint distribution when we integrate out the y. The marginal is Gaussian, easy to see. The same results exactly come out for Fy of y, except for it has a mean mu y and it has a standard deviation sigma y. Next, we want to show that the conditionals are also Gaussian. So we've seen that the marginals that come out of a joint bivariate Gaussian are Gaussian. Now we're going to just show that the conditionals, when I condition on one of the two variables, x or y, from that joint bivariate Gaussian, we're going to show that that result is also Gaussian. So I'm going to look at the conditional of Fy given x, and the reason I'm doing that is because I've already just gone through the proof of finding out what f of x is. And again, I'm going to go and use that modified, that kind of alternate form for the joint probability density function fxy. So those are equations 3 and 4 above, and I'm just going to plug those in together. And what happens? Well, if you remember, right, if you remember on this guy, this joint distribution did look like that marginal times something else, something that was Gaussian, something that was Gaussian over there, right? And we're going to be dividing that by that f of x. Those f of x's are going to cancel, and all that is left over is that thing that was sort of that wonky looking, that little bit unusual looking Gaussian. So this turns out to be real simple. Fy given x is going to be all that leftover stuff. That's 1 over sigma tilde root 2 pi exp of minus a half y minus y tilde, which is a function of x, divided by sigma tilde quantity squared. You can compare that to the one-dimensional Gaussian PDF form, and it's exactly the same. It is a Gaussian, so Fy given x, the conditional distribution in this particular case, the conditional distribution Fy given x is a Gaussian. It is a normal, and its mean, right? You take y minus the mean. Its mean is mu x, right? Tilde, and its standard deviation is sigma tilde, something like that. So we could go back and replug those in so we could see what really the mean and standard deviation of this conditional distribution is, and whether that sort of makes some sense. So take a look at this. The mean of our conditional distribution, mu tilde, right? If I just plug in what I had previously done as a set of variables, was mu y, right, plus rho sigma y x prime. So what does this tell me? As I condition on different values of x, if they are correlated, if rho, right, is not 0. If rho was 0, what would happen? This whole term would just disappear. It'd go to 0, and the conditional mean would be the same as mu y, right? Nothing would change. We would just see that guy stay exactly the same. That means knowing something about x didn't help us figure out anything about or change anything about y. That would make 100% sense. But if rho is non-zero, right, that means that we are going to adjust our mean for different values of x, whatever we were conditioning on. I'll show this by some pictures here in a minute. So in this conditional case, knowing x, as long as they had some linear correlation, right, as long as they had some linear correlation, knowing something about x will help us refine our understanding of what is the mean value of y. In the same sort of way, if I take a look at the variance of this conditional distribution, right, it is, once I plug in what that sigma tilde was, it is sigma y squared, that's the variance of y, times a quantity 1 minus rho squared. Rho is always in magnitude less than 1. That means 1 minus rho squared is always less than 1. That means sigma y squared times something that in magnitude is less than 1 must be less than or equal to sigma y squared. What does that tell me? It tells me that if I do this conditional distribution, my uncertainty in that variable y, right, gets reduced based on my knowledge of x, as long as there was some correlation, as long as rho wasn't 0. If rho was 0, right, then this entire factor that we were multiplying by here, if rho was 0, I'd just get 1, and I'd see that that conditional variance was the same. It was the variance of y, and in fact, the conditional in that particular case would just be the marginal of y. It would be just a regular 1D Gaussian random variable with mean mu y and variance sigma y squared. But if there's some correlation, the overall uncertainty about y gets reduced based on how strong is that correlation. The more strong it is, the more reduction in uncertainty there would be. So knowing x reduces uncertainty in y. It also helps us update the mean of this conditional distribution of y as well. We can see this on our contour plot. So let's switch over to the other application and take a look a little bit on some of these contour plots and see if we can make some sense on that. I'm going to clean these up a bit, okay? And we will look at some examples on these. I'm going to probably pick at least initially, how about this one? So here I have a bivariate Gaussian. The bivariate Gaussian, we know, would have a marginal Gaussian in X that was zero mean and unit variance, and that the Y would also be Gaussian, the marginal in Y would also be Gaussian, zero mean, and its variance would be 9, or a standard deviation of 3. We have in this particular case allowed there to be some correlation between these guys. What does this mean? That means that as I know something about X, it's going to help inform something about Y, because it's a positive correlation. As X gets bigger, I'd expect Y to get bigger. Okay, so what does a conditional distribution conditioned on X mean? If I say that I condition on something like X equaling 1, that means I would follow along the X equals 1 line, right? I would just slice that mountain along there. And what do I notice? I notice that I'm slicing that mountain, right, kind of at an angle. And we already knew that this thing was aligned like this, right? This major axis was aligned like this. So the peak of that slice, whoops, I probably have that just a little bit off. Let's see if we can get that a little bit more accurate. So if I come in here at 1, it should be about 3, something like that. So we're going to get something like that. That's the line in there. It's that sigma y to sigma x. That's that slope of 3 ratio, something like that. If I slice that through, the peak of where that slice is, and we know the peak for a Gaussian is where the mean is, right? Is now different, right? It is something that has been. I'm probably not doing a very good job of this. Let's try it one more time. Let's just go our slice along X equaling 1. And if you look at what's left in there, right, we are going to have something that is Gaussian along that guy, right? And what we can see now, that even though Y originally, right, had a mean of 0, when I am saying I know that X is 1, right, that necessarily has to nudge that conditional mean up a bit, because Y was greater than 0, we'd expect, because X was greater than 0, we'd expect Y to be greater than 0. And so we certainly see that following along, slicing this mountain down the X equaling 1 line, right, would show a peak value that would be greater than 0. That was that first equation saying that the mean, the conditional mean, is mu y plus some factor that depends on the amount of correlation. Look at what happens if I'd gone to something that had no correlation, right? Here I'd run my line along here, right? There's my line along X equals 1. And if I look at how the Gaussian was fit in there, right, we see that that guy's balanced in the same way. And its peak just still falls along 0. No update needed because there was no linear relationship. We could even see this more over on this side if we went along the X equals 1 case, right? So we put that guy in there as well. And we go ahead and put our distribution. Whoops, this thing is not totally doing that well. But I put my distribution in that guy. So put my distribution in there some way. I can see that that mean is coming out something different. It's something greater than 0. Okay, what else did we say? We said that based on the amount of correlation in here as well, right, when we do this conditional, that it could reduce the variability in our random variable as well. So something along those lines. Well, let's take a look at that as a general idea. So I'm going to come back over here to something like this first plot, and I'm going to go ahead and grab this guy. Let's take a particular value of x, okay? And if I look at that value x, let's do it over here. Let's do it over here. Let's look at this x equals 1, something like that again. We said we took that slice, and you look at that slice in profile, it is Gaussian. We'd already proven that. We saw that its mean, right, is going to be now no longer 0. It's going to be north of 0. It's going to be a large positive number because there's a positive correlation. But take a look at this, kind of where the bulk of that probability is, right? Where the bulk of that guy's probability is going to be over a shorter interval than what the bulk of the probability is, right? That's from these guys here. It's going to be different than the bulk of that probability that we would have seen if there had been no conditioning on x. So the marginal on just y, right? It has the bulk of its probability sitting there, maybe -6 to 6. And if I look at this one condition, so following along this line, just where there's the contours, and I probably made that just a little short, that interval there, right? That interval there is smaller, right? We get a smaller interval on that guy. So we reduced the variability by knowing something about why. So all of those we're seeing in what we had seen back in the notes. So just a very quick recap. We've been studying bivariate or pairs of random variables for some time. We know that there's lots of possible families in there. One particular and special family that's of particular interest, just like it was in the invariant case, is this idea of a Gaussian, a pair of Gaussians. We can represent the joint distribution of a pair of Gaussian random variables through this thing called the bivariate normal or bivariate Gaussian distribution. I gave the probability density function for that. We showed that the shape of that and how it depends on parameters mu and sigma, and then also that correlation coefficient rho. And we also showed that the marginal and conditional distributions that result from that bivariate Gaussian all stay Gaussian. A few final comments. I will make this comment. You can read about this in the book. That parameter, right, rho of the bivariate Gaussians, x and y, is just the correlation coefficient. So rho does equal that correlation coefficient, rho xy. The proof is in the book. You can take a look at that. It's really not a surprise. We can actually see good evidence of that in the contour plots that I showed. Furthermore, bivariate Gaussians are uncorrelated if and only if they are independent. This is a little bit of an unusual case because it tells us that uncorrelated gives us independence. If you went back and you found the marginal distributions, okay, and you set rho equal to 0, you would find that the product of the marginals would give you the joint distribution if and only if when, and in this particular case, rho equals 0. So you would be able to show that. Very few random pairs of random variables would have this particular case where uncorrelated gives us independence. Gaussians do. Okay, so that really does finish out our work in the bivariate case. So looking at things that were like pairs of random variables, we'd like to move to more than two. So many applications, so many situations in electrical engineering involve many random variables, and we need to be able to handle more than just taking things pairwise. So this next little section, we're just going to get kind of barely started on that today. We're going to be looking at this idea of what are called random vectors. This is just generalizing the bivariate case to n random variables. We're going to do this very quickly. We will describe these guys with a multivariate joint either cumulative density function, probability mass function, or probability density function. Bivariate was a joint, right? CDF, PMF, or PDF. We're going to do that again. We're going to do joint CDF, PMF, or PDF. It's just now instead of being a function of two variables, it's going to be a function of n variables. In the CDF case, we're going to take x1 through xn, right? And it's just the probability that each individual variable is less than its particular observation. So x1 less than little x1, all the way up through cap xn being less than or equal to little xn. It gets boring writing all of these lists of x1 through xn, so we'll adopt a vector notation, x under bar and little x under bar. That's just a more compact notation for saying the same thing. Similarly, we can have a probability mass function. That probability mass function is for discrete multivariate cases. So having n discrete random variables, and we have a single distribution to rule them all. So a joint probability mass function piece of x1 all the way through xn of the observations little x1 through xn. And that is just defined as the probability that the first random variable is that first random observation x1 all the way through x cap xn being equal to little xn. Again, we can utilize a vector notation in this thing to make things easier to do. So just call it piece of x underscore of little x underscore. So it's the probability mass function of vector x of vector observation little x. Probability density function joint across multiple variables, same sort of thing. I'm going to use a little f going x1 through xn of little x1 through little xn, and we can get that by doing a partial, right, a derivative of our joint CDF with respect to each one of those variables, x1 all the way through xn. Notationally, we will just let that again be f sub x underscore the vector x of the vector of observations little x underscore. all the things that you would expect for a valid probability density function, probability mass function, or a CDF hold. All the expected properties. We don't have to go through all these. Probabilities need to be greater than zero. Probability density, probability mass, or probability of events. They all have to be greater than or equal to zero. If I take these valid probability mass or probability density functions and I sum them up or integrate them up over the n-dimensional space, they have to sum to 1. Total probability still holds into play. I have to get 1 out of all of those. Vector notation wise, we've already seen starts of this, so we will adopt some vector notation. X underscore is just going to be a vector, x1 through xn. We oftentimes represent this as a row vector, but it's probably more mathematically convenient to have them as column vectors in the way we do our operations. So the way we get around that is we just show it as a row vector and then we transpose it. So that little t there just means transpose, and it really means that the way we normally represent these vectors is as a column vector. So cap x underscore is the vector of it's a vector of random variables x1 through xn. Little x underscore, right, which has elements x1 all the way through xn, and we can write that as a row vector and then transpose it. It becomes a column vector. That is my sample vector. Those are the observations of each one of those random variables x1 through xn. Okay, so we've seen this idea that we can up the dimensionality of a problem from single dimensional to 2. That was kind of chapter 5, going to pairs of random variables. And now we're going in chapter 8 to n values or n number of random variables. We can also do some additional extension on that. We can consider pairs of random vectors. So instead of an x and a y, right, we're going to talk a vector x and a vector y. And we can get joint distributions of these as well. You might wonder why we do this. It has its roots and its utility really in sometimes a signal kind of analogy. That there's a whole bunch of stuff in engineering where I have some input x and out comes an output y, right? So there's some reason to keep separation of those guys, but they might also depend on one another, and there could be multiple values of each. So this x and y might be like the inputs and outputs of systems, something along those lines, as taken as vectors, something along those lines. Okay, so what do we do in those cases? Well, we still get all the stuff that we'd expect. Let's look at the CDF. The joint CDF for the random vectors x and y as an observation of all the observations of x and all the observations of y is just this CDF going variable x1 through xn, y1 through some maybe different length ym, and all of their individual observations. If you look at the dimension of each of those, x was of length n, so that guy was an n, so it was a column vector, so that's an n by 1 vector, if you will, and y was an m by 1 vector. And so when I take them together, I'm going to get an n plus m dimensional system. So this f here has n plus m random variables involved in it. It's basically a concatenation of the vectors x and y. Concatenation just means you hook them together. We could call that w and just hook the two together, make a single vector if you wanted to. It makes sense in many applications to leave them separated. We can do the same sort of stuff for a probability mass function and a probability density function between pairs of random vectors. That's all similar as well. Okay, we're almost done with the lecture. Let's look at one example that looks at, for example, a pair of random vectors. This is really me playing with quiz 8.1. So if you're doing reading along in the book, you should be reading in chapter 8. Quiz 8.1 is given there to let you have a chance to try your hand at some of the problems involving these random vector stuff. The reason I'm picking this one to do in class is because I think they made a bit of a mistake in here, probably an oversight. They say find the distributions under these conditions. We'll look at it here in a second, but really it only holds for a very specific value of p, and they did not say what that specific value of p is. I'll probably give you a homework problem to say what value of p does this hold for, but let's go ahead and move forward with this. It looks something like this. We're going to have a random vector x that's comprised of 3 things, a random variable x1, a random variable x2, and a random variable x3. I'm also going to look at a random variable y that has its own 3 random variables, y1, y2, y3. So both of these are random vectors. And what I'm going to allow is I'm going to allow y to be derived from x. And it's going to be derived through x through a matrix multiplication. So I'm going to get this new random vector y, right, from the random vector x multiplied by, we're just going to take this matrix A, which is defined as having the top row is 1, 0, 0, the next row is minus 1, 1, 0, and then the final row is 0, minus 1, 1, something along those lines. So the problem in the quiz goes something like this. Find the probability mass function, right, for random vector y if we know random vector x, px of x, and it has some particular distribution given here. It's basically 1 minus p cubed over p cubed times p raised to the x3 when x is less than x2 is less than x3, and x1, x2, x3 are all taken from the integer set and 0 otherwise, okay? So we want to find the resulting probability mass function given this starting probability mass function of random vector x. Some things I might notice. If I have an expression that tells me how I can get y from x through a, I could just multiply both sides of that by a inverse, right? And so that's something we will rely on here in a moment. I can also just start plugging in what I know vector y and vector x and matrix A are. So I'm going to go ahead and do that now. So here's my vector y just written in its vector notation. Here's my vector x written in its vector notation. And there's the matrix A, which happens to be a 3 by 3. And we really do need it to be sized that way for the linear algebra math to work out here. You will see that in this next section, we are going to make more extensive use, actually, of some linear algebra concepts. It's just going to be an efficient and easy way of doing it. So what do we get in this? If you look at y1, for example, what is y1? I take this guy here, 1, 0, 0, and I'm going to multiply it by my vector there. So I'm going to get 1 times x1 plus 0 times x2 plus 0 times x3. That is just y equals x1. So y and x1 are the same. If I look at y2, I take the second row, right, and I multiply it there. And so I'm going to get x2 minus x1 as being y. And y3, similar kind of an idea, I get x3 minus y2. If you take a look at that, we knew from constraints in the original x that x2 had to be greater than x1. But if I take the difference of those guys, so let's say x1 was 5, then x2 would have to be 6 or more, right? If I take something 6 or more and I subtract 5 from it, y2 will have a range space going from 1, 2, 3 going out to infinity. The same thing is for y1, the same thing is for y3. So y1, 2, and 3 are all just taken from the regular integer sets, 1, 2, 3 going out to infinity, no other restrictions. If you looked at what our original distribution was, fx of x, it had this kind of wonky starting point. We had x1 less than x2 less than x3, so there was that additional constraint in addition to those guys being positive integers, something along those lines. So this transformation had sort of an interesting result. It somehow kind of got rid of any of these strange relationships like we saw with x1, x2, and x3. y1, y2, and y3 just need to be integers, something along those lines. Okay, so we wanted what? We wanted the probability mass function for the random vector y. So that is py of y. What is that? We already said what it was. It's just the probability that y equals y1, y2 equals little y2, and y3 equals little y3. But what is y1? It's just x. So that's the probability that x equals y1. And what is y2? That's just x2 minus x1. And what is y3? That's x3 minus x2. So we're just plugging in what we know y1, y2, and y3 are. Why do I do that? Because that turns this probability mass function from something unknown into something, right, that is going to be known, because I'm now dealing with some probabilities that involve x's, and I have the probability mass functions for those guys. Well, if x1 equals little y1, I can plug that little y1 in for this guy, and I can bring it over to the other side, and that says x2 has to be y1 plus y2. And x3 in the same sort of logic has to be y1 plus y2 plus y3 if I make a double substitution in that. We could have seen this result anyway by going back to our linear algebra. We had before that y was equal to ax, right? The vector y was equal to the matrix A times the vector x. If I multiply both sides by A inverse, I can figure out what x is. X is A inverse y. And if you do in MATLAB or your favorite package, you could compute out the matrix inverse to our previous A, which was given up here as 1, 0, 0, minus 1, 1, 0, and then 0, 1, negative minus, and then a 1. If you do the inverse on that with your favorite package, you find out you get this. You get a 1, 0, 0, 1, 1, 0, and a 1, 1, 1. And that's all getting multiplied by y. Well, throw in your values of what y is, right? Y, this guy here, is just something like a y1, y2, y3, something like that. And if I was interested, for example, in the second one, right? So that would be x2. What is x2? x2 is 1, 1, 0 times y1, y2, y3. So x2 is going to be y1 plus y2. Well, that's exactly what we had. And if I did the next line, I would get x3 as being y1 plus y2 plus y3. That's this guy. So it just turns out, because of the math involved here, it's actually pretty easy to solve for what is x1, x2, x3 in terms of the observations of the y1, y2, y3. Okay, so what does that tell us? That tells us that our joint probability mass function py of y, right, can be gotten from the probability mass function of x. We knew that was 1 minus p cubed over p cubed. Go back up to what that guy looked like. There was, in this case, right, there was a 1 minus p cubed over p cubed. There's also p to the x cubed. But what is x? Not x cubed, it's x3. So, but what is x3? x3, though, is just y1, y2, y3. So I'm going to substitute in x3 for y1, y2, y3 because I want something that's a function of y. And what values of this does it work for? We had already computed that out as well. The values y1, y2, y3 are just integers, non-negative integers, positive integers going from 1, 2, 3 without restriction. That's this guy. And it would be 0 otherwise. So we got this just through some math and some observations. This turns out to be just a product of 3 independent geometric random variables. The way I can probably find that is by showing what the marginal distribution of any one of these values, y1, y2, or y3 is. So let's just quickly do that, and then we'll be done with the lecture. So we can easily find marginal distributions by summing or integrating out whatever is needed. So let's continue this previous example, right? Let's find the marginal distribution of y1. I had set up here that this was a product of 3 independent geometric random variables. If you have independent random variables, the joint distribution, even if it's a vector one, we'll see this formally next lecture, it's just a product of all the marginals. So what I'm really saying here is that each of the marginals should be a geometric. We can get that marginal by what? Py1 of little y1. We just need to sum out the variables of non-interest. We're only interested in y1. That means I have to get rid of y2. So I have to sum out over the range space y2, and I have to sum out over the range space of y3. Because this is a vector now, the number of sums or integrals I have to do could get quite large. If I had a 100-dimensional vector, right, and I wanted to find just py1 of y1, I would have to have a 99 deep summation or a 99 deep integration. What am I integrating or summing over here? Well, just the joint probability model, which I'd already gotten up here. Well, in this particular case, I noticed that this first thing, 1 minus p cubed over p cubed, is not a function of any of the sum variables. I can pull that out. Furthermore, p to the y1, y2, y3 all added together, this piece can be written out as a py1 times p to the y2 times p to the y3. That's just rules of exponentiation. Py1 not being a function of the sum variables can be pulled out as well. So I'm going to get that guy pulled out. And then I'm just left with these two pieces. So I'm going to have a sum on y2 going from 1 to infinity. That's its range space of py2. And then there's that sum on the inside from y3 going 1 to infinity of py3. Actually, this guy was in there too, but it was not a function of the sum variable y3. So I was able to pull it out of that sum. This interior sum here is just a geometric sum. If you go through and solve that, that's p times, or p divided by 1 minus p. Same thing here, that's just a geometric sum. It sums to p over 1 minus p. And what we find out is that this p over 1 minus p, this one, and this p over 1 minus p, this one, are going to cancel out with two of the ones that are out here in front. And so I'm left with a single 1 minus p, that's this one. I have a single p in the denominator, but I'm going to combine that with this py 1, and that's just going to give me a py1 minus 1 because the other p was in the denominator. And that's true for y1 going 1, 2 off to infinity. If you take a look at your known families of random variables, you can identify this guy as being a geometric random variable. y2, y3 are the same, and so we get the result that we said, that this joint distribution of random vector y, right, was just a product of 3 independent geometric random variables, which we could have gotten by the marginals as well. Next time, independence and functions of random vectors, which we've already kind of started here as well.